Okay, let's start. It's 1400. So welcome to this next talk about some retro hardware. You might have noticed it in the retro gaming area. There was a machine with a transparent case in its replica of the machine we are actually talking about right now, the Galaksija. And with me is Thomas Scholz. He is presenting all the details of his replica and the original machine. So have fun.
So, hi everyone. Again, my name is Thomas Scholz. I am an electrical engineer. I am a free software developer. I come from Ljubljana and I'm a member of the Slovenian hackerspace Kyberpipa. I'm also a volunteer for the Slovenian Computer History Museum, and in the next 45 minutes I would like to tell you everything there is to know about a small microcomputer from the former Yugoslavia called Galaksija. As you probably guess, this talk was inspired by the previous Ultimate talks on the earlier congresses. If you haven't seen the talks about Commodore 64 or Atari 2600, I recommend you check them out. They're really great. So I guess before I start talking about Galaksija, I can't skip some historical background. As you're probably aware, in the 1980s, in the Western Europe at least, the whole microcomputer revolution was happening. New small computers using cheap microprocessors were getting increasingly popular. I'm talking about machines, for instance, from Sinclair ZX81 or Spectrum or Commodore 64, to name just a few. Unfortunately, the situation in Yugoslavia was a bit different at the time. The regime made it almost impossible for individuals to buy Western computers. Now, if you lived in the north of the country, this was not actually such a big problem. You drove to Austria or Italy, the borders were not well enforced. You bought a computer there, hide it under the seat of your car, drive back, and you had a pretty good chance of not getting caught. Actually, this was such a popular practice that one of the first computer games made in Slovenia was a text adventure on how to smuggle computers over the border. Now, if you lived further south, this practice was getting a bit difficult. You had further to drive. You also had internal borders to worry about. And so maybe knowing this, it might surprise you that Yugoslavia at that time had a teeming electronics industry. They were making mainframes, they were making workstations for businesses, for government. They were making their own semiconductors, and what components they could not make themselves, they imported from the West. There's a ton of interesting stories how they managed to do that, but maybe that's a topic for another time. So the availability of electronic components was not actually a problem. And in fact, several attempts were made by the domestic industry to make microcomputers that would mimic the popular computers in the West. Unfortunately, many of these attempts, if they managed to come further from the drawing board, they were usually much too expensive for common people to buy. And so this is kind of the environment where this gentleman on the right here, Mr. Voja Antonić, designed Galaksija in 1983 in Belgrade. He envisioned a small do-it-yourself computer that anyone with a bit of soldering experience could build at home. It had to be as simple as possible. It had to contain minimal number of components, and most importantly, minimal number of components that had to be imported from the West, since those were the most expensive ones. So this is how Mr. Antonić looks like today. Galaksija means galaxy in English and was named after a monthly popular science magazine of the same name, where it was first described. This happened thanks to this gentleman, Mr. Dejan Listanović, who was an editor of the magazine at the time. He arranged for a special edition of the magazine published in 1984, in January 1984, where Galaksija was completely described. Assembly instructions were given, schematics, PCB artwork, user's manual, and an offer was given for a kit for sale, which included the most hard to buy components like the mechanical keyboard and the CPU and the ROMs that contain the Galaksia's operating system. You also had an option of making everything yourself, and you could just send empty EEPROMs to the authors by mail, and they would program it with the operating system for free and send it back to you via mail. So since Galaksija started as a do-it-yourself computer, each one looks a bit different. Many ended up in wooden cases like this one. At the start, when the article was published, it was predicted that perhaps a few hundreds would be made by hobbyists, and in the end, the count of all the ROMs shipped via mail ended up around 8,000, so it was a much larger response than expected. Later on, the industry also picked up on Galaksija's success. They started making them on production lines. This is one example of how it looks like. This is a bit different one. Many of them ended up in elementary schools, and in fact today it's not even known how many were made. Even not the original authors were not notified of production numbers. And while it's most certain that these numbers are not in any way comparable with popular machines in the West, it's certain that Galaksija was the most popular domestic microcomputer in Yugoslavia in 1980s. If you look under the case, this is how a bit messier do-it-yourself version looked like. You had a single layer PCB, through-hole components for easy assembly. This is a bit cleaner version made professionally. If we look at what we have on the board here, there's a Zilog Z80 CPU running at 3 MHz. This is a CPU you would also find in the contemporary Sinclair computers. There's space for 4 kilobytes ROMs. The first socket, ROM A, is usually populated with the Galaksija's operating system, and the second socket usually with the first official extension of that. There's 6 kilobytes of static RAM on board. There's a character generator ROM which contains the character set Galaksija is able to display on the screen. There's a special hardware register that's called latch in the original documentation. There are also 13 other general purpose, low scale integration, digital circuits in the low power Schottky technology. So I'm talking about AND gates, OR gates, shift registers and so on. And together with a handful of analog components, this is a complete working microcomputer. If you look at what we have at the back, there's a 5-volt DC power supply input. You have an analog audio tape input and output for retrieving and saving data from audio cassette tapes, as this was the usual mass storage device at the time. For video output, you either had an option of using a radio frequency output, which you could connect to your television's antenna connector, or if you happen to have a monitor that was capable of displaying composite video, which was quite rare at the time, you also had an option of using that. And there's an expansion connector, which, as it was common practice at the time, just exposes the CPU bus. Okay, so this is how the screen looks like when the Galaksija boots up. You get a command prompt. This is a Hello World program in the built-in BASIC interpreter. To load a program from cassette tape, you type in Alt, start and press Enter, start the tape. When the loading finishes, you get the command prompt back, type run, and the program runs. So this is the original schematic that was published in Galaksija magazine. And I guess it's time to dive into the details. So first, let's look at the CPU. The Z80 CPU is an 8-bit architecture, which means you get a 16-bit address bus capable of addressing 64 kilobytes of memory. You get an 8-bit data bus. You actually have 2 separate address spaces, 64 kilobytes address space for memory and 64 kilobytes memory address space for I/O, which is completely unused on Galaksija and available for any extensions on the extension port. This is what you get inside the CPU. There's an 8-bit accumulator register, which is capable of performing most of the arithmetic and logic operations the CPU supports. There's an 8-bit status register. You had 3 16-bit general purpose registers, which can also be used as 6 8-bit registers. You get two 16-bit index registers, one 16-bit stack pointer, and two special-purpose 8-bit registers, I and R, which I will describe in a few moments. You also get a secondary register bank, which you can exchange with the primary register bank with this fast single byte instruction. This is very useful to implement fast interrupt response routines, since you do not need to push the CPU state on the stack. So CPU instructions consist of one or more machine cycles. All instructions start with machine cycle M1, in which the CPU fetches the instruction opcode from the memory, and instructions can then have additional memory access cycles as needed. Machine cycles are divided further into T cycles. This is the CPU clock, the 3 MHz clock in Galaksija, for instance. In detail, how the M1 cycle looks like. At the second clock cycle, the CPU puts a program counter on the address bus and reads a byte from the opcode byte from the data bus. And on the third and fourth clock cycles, the contents of the I and R register are put on the address bus. The CPU actually does not use the result of this memory read operation. This was a feature intended to refresh dynamic memories, as the CPU automatically increments the lower 7 bits of the R register. In this way, the CPU reads out consecutive memory locations from RAM, one location per executed instruction, and this can be used to refresh dynamic memories, but Galaksija uses a static memory, and this feature is actually used to produce video signal, as we'll see later. This is the main page of instruction for the Z80. You get 252 single byte instructions. You get 4 instruction prefixes for 2 byte instructions, and 2 of these prefixes have a further prefix for 3 byte instructions. Okay, so the CPU has a single interrupt line, maskable interrupt line. When this line goes high, the CPU finishes executing the last CPU instruction, and after that enters a special interrupt response M1 cycle. This cycle can actually be arbitrarily lengthened by inserting wait states using a wait signal. This is actually important if you want to achieve accurate synchronization of the interrupt routine. And Galaksija uses that to achieve synchronization between the video driver code and the electron beam on the TV, as we'll see later. Why is this important? Because you cannot know in advance how long the execution of the last instruction will take. There's an interesting feature in original Galaksija circuit here. It depends on the relative timings of these two transitions, so low to high M1 and low to high I/O request lines. This is not actually specified by the Z80 datasheet, and it turns out that early CPUs actually honor these timings, while newer ones usually have these two transitions much too close together for the original Galaksija circuit to work. So new CPUs will not work with original Galaksijas, or most of them at least won't work. So that's good to know if your CPU burns out. Okay, so during the interrupt response cycle, the CPU reads out a single byte on the data bus. How this byte is interpreted depends on a software selectable interrupt mode. In interrupt mode 0, this byte is interpreted as a opcode, which the CPU then executes in the next machine cycle. This is not actually useful on Galaksija, since it lacks any hardware that would put meaningful data on the data bus there. In interrupt mode 1, this byte is ignored, and the CPU always executes a restart on address 38 hex, and this is the default mode Galaksija operates in. This address is mapped to ROM, and there's some built-in interrupt routine there. There's a third interrupt mode in which that byte is interpreted as an index into a jump table, and this can be useful if you want to hijack the interrupt on Galaksija to, for instance, to run your own code. You only have to sacrifice 256 bytes to have a dummy jump table, because you cannot predict what the index will be there. Okay, so we finished with the CPU. Let's look at how the galaksija generates video signal. That's what majority of the hardware there is actually dedicated to. This is how the TV screen looks like. It's divided into the usable image area and the sync and overscan area. Galaksija uses a pulse system, which means you get 50 frames per second. The electron beam scans the screen from top to bottom, left to right. You get 56 lines on the top overscan area. You get 208 lines in the usable image area, and again at the bottom 56 lines in the overscan area. The maskable CPU interrupt fires on when the electron beam starts scanning the first scan line of the usable image area. And by default, this starts the video driver in ROM, and the video driver code executes as long as the electron beam is scanning the image area, which means that the CPU is only free to execute user code approximately 1/3 of the time. Similarly, as for instance in ZX81, you can disable the interrupt, then you have the full attention of the CPU, but unless you do some clever tricks, you cannot display anything on the screen at that time. The CPU runs synchronously with the electron beam. You get 32 clock cycles in the left overscan area, 128 cycles in the image area for each scan line, and again 32 clock cycles on the right. The pixel clock is 2 times the CPU clock, which means you draw 2 pixels on the screen per 1 clock cycle. The built-in video driver divides this area into 16 rows by 32 characters and uses a frame buffer in RAM starting at address 2800 hex. The character generator ROM contains the characters which are then filled into these character cells. Characters are 8 pixels wide by 16 pixels high. And this data is actually not mapped into the CPU address space. Rather, the part of the ROM address that determines the scan line of the character to be drawn comes from the latch, so that special hardware register I mentioned at the start. And the part of the address that determines the character comes directly from the CPU bus. How this? Okay, so and the output of the ROM, so the pixel data gets into a shift register, which serializes it. If you look how everything works, so at the start, the CPU generates consecutive frame buffer addresses using the I and R registers and the dynamic memory refresh feature. These addresses read out bytes from RAM, from the frame buffer area in RAM, so characters to be drawn, together with the character scan line that has been programmed into the latch. This reads out 8 bits of pixel data at the time from character ROM. This gets then loaded into a shift register, which serializes it and feeds it into some analog circuitry that generates the composite video. If you look into the timeline, how this works, at the top we start at the moment the electron beam starts scanning the first scan line on the screen. In the first 2 clock cycles, this is the first half of the M1 cycle, the CPU reads an instruction from ROM. It's not actually important what this instruction is, as long as it's a single byte instruction that does not do memory accesses. In this case, for instance, it's increment register D. In the second half of the first M1 cycle, this dynamic memory refresh feature gets invoked. The I and R registers have been programmed beforehand by the video driver code to point to the first character in the frame buffer area at this time. In this example, this reads out character B, ASCII code for B from the frame buffer. And together with the value in latch, which has also been previously programmed by the video driver code, this loads up the first scan line of the character B into the shift register. So the pixel clock is 2 times the CPU clock, so in the next 4 clock cycles this gets shifted out by the shift register into the composite video generation circuit on board. The whole procedure then repeats for the second character, so the R register has been automatically incremented by the CPU, and it reads out the next location in the frame buffer, and so on until the first scan line for the whole row of characters has been drawn. When the electron beam returns to the start for the next scan line, the video driver code has already updated the value in the latch so that the next scan line gets drawn, and then the next, and so on until we have the complete line of characters. So if this rings a bell, the ZX81 uses almost a completely the same routine, except that it actually executes the frame buffer contents as code, it doesn't use the dynamic refresh feature like this. So the character generator ROM contains 64 alphanumeric and punctuation characters. This roughly correspond to the middle of the ASCII table, except for the Yugoslavian accented characters there at the end and the logo that's displayed on the command prompt. You also get 64 pseudo-random characters. This allows for a kind of a low resolution graphics. Each character is divided to 2 by 3 dots, and together with the original character resolution you get a low resolution graphics of 64 by 48 dots. So this is kind of a graphics you can expect from Galaksija. This is a port of a jumping jack game that was originally made for Sinclair Spectrum, and this is how it looks on Spectrum. Also, of course, Spectrum also has colors. Galaksija has only black and white video. This is a port of the Tetris game. This is an original adventure game, Inspector Spiridon. This is a port of a dancing demon game from TRS-80. And if you manage to override the original video driver code, you can get high resolution graphics like this one. You can look, if you look closer here, actually each scan line contains a different pattern of pixels. This is done with a custom video driver that actually skips scan lines in the character generator ROM. So using this technique you actually can display a different character on each scan line, and you're only limited with the frame buffer size because Galaksija only has 6 kilobytes and you can quickly run out of memory. But on the horizontal line you're always constrained to the combination of pixels you have in the character generator ROM. Okay, that's so much for the video generation part. Let's look at what we have in address space. So at the bottom we have the 2 ROMs. Above that there's an memory mapped IO area starting at 200 hex. Above that there's 6 kilobytes of RAM. And above the RAM, the address space is unused and available for further extensions. In the I/O area, there's a memory mapped keyboard and access to the latch. If we check first the keyboard, each key has its own memory location. They are alphabetically ordered, which greatly simplifies mapping the addresses to ASCII code, which then affects the size of the code in the ROM. If you read a byte from an address associated with the key, you have to look at the least significant bit. If it's 1, the key has not been pressed. If it's 0, the key has been pressed. The first column of keys also serves as an output of an audio comparator for the cassette audio input. There's a simple analog comparator there. If the bit is 1, there has been silence on the input. If it's 0, an impulse has been detected, and this can be used to reconstruct data that has been saved on the tape. So what's in the latch? Latch only implements the most significant 6 bits, so the bottom 2 bits are not implemented. This address is write only. You cannot read out back the values you have programmed in there. So bits 2 through 5 select the character generator ROM, which I already discussed. Bits 2 and 6 control the cassette port output. This implements a simple digital to analog conversion. You get to output 3 different states, so +1, 0, -1. And this can be used to save modulated data to the tape, or if you happen to connect a speaker, so there's no built-in speaker, but you can connect it to that output, and some games use this to produce audio. And the most significant bit is interesting. It performs a RAM address line clamp. So if you write a bit 1 in there, RAM addressing works as usual. If you write a bit 0, RAM chips always see address line 7 as 1. If you think about it, this performs a simple memory map operation. If you divide RAM into blocks of 128 bytes, writing 0 into that bit remaps all the odd blocks to even blocks. This might sound like useless. Why would you want to do that? In fact, it turns out that some of the Z80 CPUs that were encountered by the Galaksija's designers did not implement bit 7 in the R register. And actually the ROM code that's active during video refresh uses this latch function to control the bit 7. Actually, I haven't seen any modern Z80 that would have this, but apparently it was required at the time. Okay, so now I guess that's all about Galaksija's hardware. Let's look at what the operating system contains. Galaksija's operating system is actually closely connected to this computer. This is the TRS-80. Contents of Galaksija's ROM were developed by Mr. Antonich on a homemade clone of TRS-80 with 64 kilobytes of RAM. He took the level 1 basic from TRS-80, disassembled it, adapted it to fit Galaksija's hardware, compiled it back into the binary that's then programmed into Galaksija's ROM-A. This is how the published disassembly looks like. It's very light on comments because not many comments would actually fit together with the source code into the 64 kilobytes of TRS-80 RAM. So, yeah, by the way, so concerning this code, you often can hear a rumor that this Galaksija's operating system is based on Microsoft Basic, and that some of this code has actually been written by Bill Gates. So while it makes for a funny story, it's, as far as I know, not actually true. As far as I know, level 1 basic in TRS-80 had no involvement from Microsoft whatsoever. Okay, so what's in ROM-A? At the start we have the 0 page, so the first 256 bytes of ROM. This contains the reset vectors, so this is where the Z80 will jump to when a maskable or not maskable interrupt happens. This part of ROM also contains entry points for commonly used Z80 functions, because the Z80 has a special single byte restart instruction which can be used to perform very efficient jumps into this area. Then below that we have the video driver, which I already discussed. Majority of the space in ROM is occupied by the basic interpreter. This is the code, that's location of the code, and there you also have some lookup functions. It's interesting that these lookup functions actually overlap with the video driver code. That's because some of the code there can also be interpreted as ASCII strings to save space. So what basic interpreter offers? You get a bunch of command line instructions. You can type only on the command line. These are used to load and save data from the tape. You also get a simple on-screen editor for the basic programs. Then you get a bunch of functions, so keywords that will return a value, and some more procedures, keywords that will not return a value. You might notice that there are also some flow control primitives there. That's because those are actually implemented in the BASIC as normal BASIC procedures. You only get 3 error messages back. What? Okay. I believe that, yeah. Okay, so what means there should be a parsing error, how invalid argument, and sorry, it ran out of space. The BASIC interpreter is actually extendable. You get a BASIC link system variable at this address at the RAM, where you can point it to additional lookup tables, and you can add additional functions, procedures, functionality of the BASIC interpreter. In addition to BASIC interpreter, there's a simple terminal emulation. It recognizes some basic ASCII control codes. You also can redirect the terminal output to arbitrary device. There's again a hook in the system area of RAM where you can point it to your own function, and you can then send it to printer or whatever other device there is. The terminal emulation also tweaks a bit the video timing, so you get a fancy smooth scroll animation when the terminal scrolls up. Okay, there's also a stack-based floating point calculator, which again overlaps a bit with the video driver there. For any floating point geeks here, there's the Galaksija uses a 23-bit mantissa, 8-bit exponent floating point format. It actually uses 2 different floating point formats. The 40-bit extended format is used for performing calculations because that's easier to do. And for storing values into RAM, it uses a compressed 32-bit format. RAM also contains some keyboard driver functions and lookup tables to map scan codes into ASCII characters. There's an audio cassette driver for loading and saving data. And in the end, you get at least exactly 1 spare byte, and that's quite amazing if you look at it. Okay, so what about RAM? At the start of the RAM, you have the system area. Most of the system area is occupied by the frame buffer, which I already mentioned. It's 512 bytes. Below that, there's space for 26 basic variables, so floating point variables for each letter in the alphabet, and 2 string variables with the maximum length of 16 bytes. You also get the arithmetic stack for the floating point calculator, and the same area is occupied by the CPU stack, which grows in the other direction. There's also some general purpose buffer that's used by the BASIC interpreter, and this leaves you with around 5 kilobytes of RAM left for user space. In the user space, this is how things are usually divided. So this part starts at 2C3A hex. At the top, we usually have a machine code program, if any, if your program actually uses machine code. Below that, there's a basic program, which is pointed to by 2 system variables, basic start and basic end, and this program grows downwards. And on the other end of the RAM, we have a numerical array for basic and a string array for basic, and these 2 grow upwards in the other direction. Some other useful memory addresses that come in handy when programming Galaksija. Since Galaksija uses software to produce video signal, you can affect the position of the screen by poking 2 system variables. So you can affect the horizontal and vertical position using, if you write to these 2 memory addresses, 2BA8 and 2BB0 hex. Start and end of the basic program I already mentioned. There are 2 system variables that take care of that. And if you intend to use assembly, you have to take care about the IX register. This is solely used as a stack pointer for the floating point calculator. So if you want to use any ROM routines in your assembly program, you have to take care not to modify that. Same goes for the IY register. This is used as a interrupt hook. So if you point it to your own assembly routine, it will get executed 50 times per second just after the screen has been refreshed by the video driver. Okay, finally, let's look at the how Galaksija stores data on the tape. This is the modulation that's used. It's very simple. A single pulse encodes a bit 0. 2 pulses encode a bit 1. This gives you a kind of a slow modulation of 300 bits per second. So if you're familiar with, for instance, Sinclair Spectrum uses frequency shift keying, which gives you around 1,500 bytes per second. So this might at first sound slow, but if you think that Galaksija only has 6 kilobytes of RAM to work with, it's not actually such a big problem. But on the other hand, decoding this only takes like 200 bytes in ROM, so that was the decision that was made by the programmers. What's actually stored on the tape? Each tape block starts with a sync byte that's always A5. Below that there's a 16-bit start address and 16-bit end address, all in little endian, since Z80 is little endian architecture. That is followed by the actual data to be loaded, and in the end a checksum. And you have to take care that the sum of all bytes, including the checksum byte, ends up FF hex. So if you think about it, this is how this gives you a general mechanism of overwriting arbitrary locations in the CPU address space from the tape. So how usually Galaksija's programs use this. This is also the way ROM code will store data on the tape. So the majority of the data will get loaded, of course, into the user space, starting at 2C3A. But the data will start loading 4 bytes before the start of the user space. It will override these 2 system variables, basic start and basic end, and it will set them so that they point into the user space to the location of the basic program that was loaded there. Now, Galaksija has an intentional feature that when you load data from the tape using ROM routines, it will always return back to the command prompt. This was kind of an intentional feature for anti-copy protection, because the authors wanted programs to be shared. So when you loaded a program from the tape, you could always save it back to another tape instead of running. So this is kind of a difference from other machines like that, which will give you a option of starting a program automatically as soon as it's loaded. Of course, it didn't take long for people to figure out how to circumvent the anti-copy protection feature. What you usually encounter with programs like this is they start loading data even a bit further into the system area. They overwrite the video link pointer. If you remember, this is the terminal redirection pointer. They change this pointer so that it points to some code they loaded into the user space. And when Galaksija finishes loading data, it will attempt to print the command prompt. The calls to the terminal emulation layer will get redirected into the user code, and then that code can do whatever it wants. It can usually some people use this to have custom loaders for faster loads and stuff like that. But it's not very common. Okay, let's talk about upgrades. I already mentioned the first official upgrade. The ROM-B added a Z80 assembler and development tools. This made Galaksija later very popular as a development environment for embedded Z80 systems. It also added additional mathematical functions and some additional basic extensions, which mostly dealt with hardware that you could connect to the extension port at the back. There was also a Galaksija Plus. This was actually released a few years after the original. It added a true high-resolution graphics mode, dedicated audio hardware, I think 48 kilobytes of RAM, but it was not actually popular, and today you will very rarely encounter one. So if you want to play with Galaksija today, the easier way to start is to get an emulator. There's an emulator for Windows, there's an emulator for DOS, there's an emulator for Sinclair Spectrum, and there's an emulator for Sam Coupe if you happen to have one of these around. Actually, none of these emulators are cycle exact, so they will only run software that depends on the built-in ROM video driver. If programs mess with the video timings, like the demo I showed before, this will not usually work correctly. For that, you need a hardware implementation, at least until somebody creates a better emulator. Hint. So the simplest hardware implementation is a micro Galaksija. This one puts everything on a single FPGA chip, the Z80 core, all the memory, and all the logic. There's a PLD implementation. This one keeps a separate CPU and memory, but implements some of the logic in a programmable logic device. And there's a CMOS implementation, the one you could see above on the Congress in the retro gaming area. And this one retains all the nature of the original in having all the logic in discrete chips. For the cost of one additional logic chip, it also fixes the Z80 timing issues I mentioned at the start. So this one will actually work with any Z80 you will find these days. Okay, so now we want to develop software for Galaksija. The basic tool is an assembly. If you, of course, want to go further than just basic, which is quite limited. There's also this assembler also comes very handy. The Z88 development kit contains a C compiler which has been ported to Galaksija, so you can now also write code in C and compile it there. And of course, if you intend to develop programs for Galaksija on a PC, these Galaksija development tools come very handy. They allow you to emulate the cassette player through your PC sound card, so you can conveniently transfer code and data between your PC and Galaksija. Further information about Galaksija and hardware there. The Z80, home of the Z80 CPU contains all information about the CPU you ever wanted and more probably. There's an incomplete ROM disassembly available on the net, which is pretty complete at this point. There's a collection of original software which you can load into the emulators or some hardware implementation. If you happen to speak one of the languages from former Yugoslavia, you can get a ton of original magazine scans that cover all aspects of Galaksija. And if you happen to speak English, then over the time I published many blog posts about various minor details of the original Galaksija circuits on my blog. And yeah, there's also a forum, which unfortunately is not very active these days, but it's worth mentioning. So that kind of concludes my presentation. I hope I managed to satisfy your curiosity about Galaksija. And
yeah, thank you very much. If you jump up and enjoy and have a question, please head over to the two microphones, which some people might want to do. Yeah, we started. Do we have any questions from the internet, by the way? No questions from the internet? Then, well, go ahead.
Okay. Hvala mnogo, vrlo dobro je bio. The software that was used, you mentioned a lot of games and a lot of techniques that were used for gaming development. Was there any sort of office or production software that was in common use?
Not that I know of. There's a lot of software in that collection which has an unknown purpose and without documentation and stuff like that. Galaksija has been popular with the amateur radio community also. There's some software there that I guessed it had to do with some amateur radio stuff, but documentation is often lacking, so you get code, you don't know what it does.
Thank you.
Go over there.
Oh, hi, yeah. You mentioned the pixel clock is double the CPU speed.
Yeah.
How is that achieved?
So there's a clock tree. You generate a 6144 kilohertz clock with the crystal, and then that's divided down by 2 to 3000. So 72 kilohertz clock for the CPU, and that gets further divided down to get timings for the vertical sync and horizontal sync.
Okay, and overclocking the CPU is not really successful, I guess? Or?
The problem here is that the CPU must run synchronously with the electron beam. So if you overclock the CPU, you will get more than 50 frames per second, and TVs won't actually display anything there.
Okay. It's a normal composite video signal?
Yeah. So it's the original Galaksija actually had some weird features in that signal that modern LCD TVs won't display properly. That CMOS replica I made fixes that, so you can plug it into a modern TV and that works.
Okay, thanks.
Hi, I wonder if there was any usage for bulletin board systems. So is there software for it, or is there a serial interface in any kind?
There was an article published on how to control a modem through Galaksija. So there was some usage of that, but I'm not familiar how extensive that was. I remember an article that had a picture of this acoustic coupler next to Galaksija. I don't really remember if there were any BBCs or something mentioned.
You said there were memory regions both used as code and strings. Can you say something more about that?
Yes, so if you recall when I was discussing the video driver, how the video driver code works, it's not actually important what the CPU executes while the electron beam is scanning the scan line. It's only important that the instruction is a single byte instruction with no memory accesses. And it turns out you have space for 32 single byte instructions while the electron beam is scanning the scan line. And this leaves you plenty of space to perform operations you need to do so that you can prepare everything when the electron beam scans back to the next scan line. And there's also some space left for instructions that don't need to have any purpose. And those were actually used as ASCII strings. So if you look at the disassembled code, it actually adds ASCII strings there and then corrects whatever damage that code does to the register and stuff like that.
Thank you.
Hi, I have a bit different question. I come from Croatia, and this is great, but I've never heard of this computer before. So since you work at the museum, maybe you can tell me more about the modern reception in states of former Yugoslavia, in formal education and in popular culture, maybe. Why is it not that famous?
So actually, I don't know how to answer that. Slovenia, actually, it was not where I'm from. It's not actually, the Galaksija was not actually that popular because people rather got a Spectrum or Commodore. I happen to recall that some of Galaksijas, I've seen Galaksijas in elementary school. So why they're not so well known today? I personally first kind of got interested in Galaksija when we got one to our museum, and that was, I don't know, a few years back. So
yeah, it was just interesting because, well, now we hear lots of popular culture from Yugoslavia, music and everything like that, and I know computers are not that popular, but this would really be popular if people knew.
So there's the computer museum in Croatia in Rijeka, the Pick and Poke one. They have a few Galaksijas there. They're happy to discuss that. As I said,
okay, thanks.
Okay, I don't see any more questions. Then another warm welcome of applause for the speaker, Thomas.